Today we are going to focus on the differences between linear functions, which you're very familiar with, right? And nonlinear functions, but not just any nonlinear functions, because parabolas are nonlinear, absolute value is nonlinear. We're specifically talking about exponential functions. The hockey stick, the banana, whatever you want to call it. They swoop down like a bird at the ocean trying to catch a fish. If you've ever seen that, it's amazing. Or a hawk trying to catch a mouse in a field, if you've ever seen that. Kind of like the takeoff pattern of an airplane, right? Not exactly, because they're going to level out, and the exponential functions do not. They increase rapidly, they decrease rapidly. So, whoa, I did not clear these off. On your notes, we are going to talk about how they look differently on tables, on graphs, in equations, and in words. So let's start with the linear model. Describe in words the rule for each type of growth. Well, the y-intercept is 6. And then the 5 is a rate of change, or we often call it the slope. But on the exponential model, although it starts out similarly, the 6 is also the y-intercept. The 5 is the rate of decay or the rate of growth, not a slope. And as we've seen over the last few days, it really is rapid decay or rapid growth, whereas the linear model is more gradual. It's a straight line. Okay, the second line down says, identify which kind of sequence corresponds to each model. I'm not really sure what that means, but what I noticed is that the linear model is adding, and the exponential model is multiplying. And it's hard to see well, almost impossible to see in the equation, really, but it's going to stand out in the table of values. So let's look down at the linear model. We decided the y-intercept is 6. Actually, we said that's the same for both of them. So I'm going to make up a story so it's a little easier. Johnny has $6 in his bank account. He can make $5 every time he mows the lawn of their house. So after he's mowed one lawn, now how much money will he have? 11. After 2 lawns, 16. Like I said, this pattern is we're adding $5, adding $5, adding $5, adding $5. And that would continue. The exponential model, I don't know anybody who gets paid allowance like this. We know the y-intercept is 0, 6. And we know the pattern is multiplying by 5, but I like to use the equation so you can see where that comes from. So I'm going to plug in a 1 for the x. 5 to the power of 1 is 5. 5 times 6 is 30. And now I'm putting a 2 in for the x. 5 to the power of 2 is 25. And 25 times 6 is 150. So the faster way to do this is to notice that we are multiplying by 5. So we would then multiply by 5 again. Of course, I don't have my answer key with me, so let me go grab my calculator. 150 times 5. Yeah, can you imagine if your parents paid your allowance like this? This would be fantastic. You could have your college semester paid for in 4 hours. Depending on where you're going to college, I suppose. Okay, so as I'm looking at these 2 different table of values, if I'm trying to make an observation, oh dear, my shirt today is like touching the board and making it think I'm moving things around. Okay, if I just saw these table of values and I needed to decide if they were linear or exponential, I'm noticing that 6 times nothing gives me 11. Well, that's not true. It would be a decimal. But 6 plus 5, and then I check it, plus 5, plus 5. So again, adding, 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 adding. If I think this one is adding, I could try it. It could be plus 24. But is 30 plus 24 150? No. Times 5. Multiply, multiply. Okay, what if these numbers are getting smaller, though? What am I adding or multiplying to make it smaller? Well, on the linear model, you could add negative numbers. That could make it be smaller. But it's not negative numbers that make the exponential function smaller. Hopefully, are you thinking in your brain what it makes them smaller? It would have a rate of something like a fraction. If you multiply by a fraction, your numbers are going to get smaller. Okay, this graph is kind of tricky because there's no numbers. But we've got to get up to 26. So 3, 6, 9, 12. Okay, and if you do big enough dots, it's going to look pretty accurate. So 0, 6, 1, 11. After 2 days, it was $16 when we were talking about Johnny and his money. And this would just continue in this beautiful straight line. All right, there's no way we're going to get to 3,000. Let's just try to get to 750. I don't even know. 100, 200, 300, 400, 500. Okay, over 0 up 6. Over 0 up 30. I said over 0. I meant over 1 up 30. Over 2 up 150. Over 3 up 750. And there's no way I could manage to create a graph that goes up to 3,750. So it swoops up so fast like that jet. They're so impressive and cool looking. Okay, so if you see a graph, you are looking for two things. This is a straight line. This is a curved line. It's a hockey stick. It's a banana. It's a bird. It's a plane. I don't know. When I'm looking at the tables, adding, adding, adding is linear. Multiplying, multiplying, multiplying is exponential. And then these formulas might be the trickiest. Is this equation linear or exponential? Write it down. Commit. Oh, my shirt today. Got to roll my sleeves up. What makes an equation exponential or linear? What is it? Is it that it has an exponent? Is that all it needs? No. On an exponential model, the variable is the power. The variable is the power. In the linear model, the variable is in the base. Now, if you're unfamiliar with those vocabulary words, when we learned about exponents, we do something like this, and we say this is the base of the exponent, this is the power of the exponent. The whole thing is called an exponent. We use the terminology incorrectly a lot. So to be exponential, to show exponential growth, the variable, the x, the t, those are the most common ones, it's in the place of the power. It's the tiny number up high. And to be a linear model, the variable, your x, your y, your v, m, n, o, p, whatever they choose, is in the base. So now that we've narrowed that down, is this over here in my blue or in my red cloud? Is that a linear model or an exponential model? So the 3 squared is just a 9 in disguise. This is linear because the variable is in the base. Okay, here's a couple examples that we did. Does this table represent a linear or an exponential function? Explain. So we did this in class, which I forgot to record. So fun. So I get to do this by myself. And students noticed that it was either -2 or ×3. The -2 pattern does not hold. This was exponential because we had a multiplying pattern. B, answer in your head, linear or exponential? Linear, and why? Well, the reason that I just stated is because the variable is in the base. The variable is in the base. All right, two more. A, linear or exponential? Explain. Most people noticed that it was adding 2, adding 2, adding 2. So this is linear because the pattern is linear. It's going up by 2 each time, which is an adding pattern. Is B linear or exponential? Answer it in your head. It's going to be exponential because the variable is the power. It's the power. Okay, hopefully that woke you up if you'd fallen asleep. Good luck with your homework. It's cutting and gluing, which is so super fun.